Okay, today we're going to talk about numerical diffusion and also this artificial diffusion, and also about computational modes, although those unphysical modes that can be introduced into numerical solution by using finite differences. So generally in our field, in meteorology, atmospheric science, and oceanography, we deal with a fluid which is characterized by very relatively small dissipation of kinetic energy, so it's not very viscous. That's why we have all these eddies and all these waves in atmosphere that can last for many days or considerable amount of time, even small ones, with no visible sign of kind of dissipating overall. So it's not like we deal with some very viscous fluid, like for example some oil or honey, something like that. So our equations are mostly hyperbolic. Hyperbolic, remind you, it's advection equation or wave equation, and they're not dominated by parabolic equations, which are diffusion equations. So that's why it's very in our field most important process that we really concentrate when we create finite difference approximations of our original differential equations, that we mostly concentrate on approximative parabolic equations. Usually our diffusion operators are kind of secondary in nature, because most important process for us is advection of stuff or transport. So in previous lectures, when we talked about finite difference approximation of advection equation, we we have shown using Taylor series that by moving from calculus to algebra, we introduce additional terms to our equations, differential equations, that contain higher order derivatives, so higher than order 1, so second order, third order, fourth order, and so forth. So they have, some of those have even order, some of them have odd order, but there are like a bunch of those terms. And so today we're going to talk about either some general rule to understand what kind of processes, unphysical processes, we're introducing to the system by moving from calculus to algebra. So let's consider this our example of advection. So we have advection equation d phi dt plus c d phi dx. So this equation just describes again a transport of some quantity with velocity c and its constant velocity, and this equation is not diffusive. I mean, it's not dissipative, amplitude is preserved, and it's not dispersive. All modes, regardless of wavelengths, are transported with the same velocity c. So this is our differential equation. But when we move to algebra, to numerical representation of this equation, we have shown that, so this is calculus, and this is our algebra. We actually move from this equation to equation where right hand side has bunch of terms like some n order derivative of phi, and here it could be like delta x, say n minus 1, and so on. So this is our truncation error, and also they could be terms with delta t, so it's generally a function of our delta x and delta t. So this is our truncation error, and So when delta x and delta t reduced, this truncation error becomes smaller and smaller. We discussed that too. But it's still present because we never go to really, really small delta x and delta t. So they're always present. And so let's now discuss how these various orders, these various derivatives here affect our solution. So let's consider this kind of general equation. So we have d5 dt equals to some coefficient and nth derivative of phi. So what this equation, so this is one of those terms, and because it's linear, the effect of various terms is basically superposition of those solutions. So let's consider our general solution, which is Fourier mode. It's e power I omega t, kx minus omega t. So k is wave number, omega is frequency, x distance, t is time, and amplitude is 1. I just normalized. So if we now plug in it here, what we get? We get minus I omega, and we will cancel immediately this e because it's on both sides is going to be the same. So we get minus I omega equals to a times ik to the power of n. We differentiate n times this function. Yeah, that's it. So, and now let's divide by minus I. We have omega equals to minus a I power of n minus 1 k to the power of n. So this is our dispersion relation. So you see, depending on n, we have different dispersion relations. So for n equal to 1, which is our solution here for our original equation, we see that now I in the power of 0, it vanishes and it becomes k. So omega divided c equals to omega divided by k. And in our case it becomes kn minus 1 here. So for n equal to 1, for our original equation, you see that this vanishes. So we have some constant. So our velocity, as we talked before, is constant. But for our truncation error, we have n greater than 1. So n is here is from 2 to infinity. And for for n greater than 1, 2, 3, and so forth, we have different dispersion relations, and we see that our c now for n greater than 1 starts depending on k. So c is a function of k, of wavelength. So we have dispersion. Even though originally we had no dispersion on this equation. So now we introduce some dispersive waves. Our waves of various wavelengths starts moving actually with slightly different speed than dictated by this equation, which tells that they should move with the same speed. So we have dispersion right away. We see from this equation. Now, how about diffusion? Or not diffusion, dissipation. Dissipation is a change of amplitude. So now let's see if we have two cases. So let's consider two cases. So we have n, let's say odd numbers. So like for example, 3, 5, 7, and so on. What in that case? When we have odd number, then I in the power of fn minus 1, it becomes so it becomes I to the power of even, so n minus 1 is even number, and then this guy is equals, actually can show as n plus minus 1 in the power of n plus 2 divided by 2. So now it's real number, which means that our dispersion relation, that our C is actually real. Means that C is real, and it means that it's propagations. There are propagation waves. And it means that omega is real, which means that we still have the same waves. Omega is real number, so this still remains the same, so amplitude doesn't change. So no change in amplitude. Still sine waves moving right or left. So that means that for odd derivatives in our truncation error, we have only dispersion. So it's dispersion only. So odd derivatives in truncation expansion make waves move faster or slower depending on their wavelengths, but they don't affect amplitude of waves. So now let's consider another case when n is even. Like 2, 4, 6, and so on. What's in that case? In that case we have I to the power n minus 1. It's equals to some sign here, but it will be some real number times I. So it's going to be imaginary. Imaginary number. So our C is imaginary and omega is imaginary. So omega equals to some I times some omega and number, which means that if you substitute in this equation, you have phi equals to phi e to the power of ikx times e. Now if omega equals to this, I, it's going to be minus I omega, oh no, I is gone, omega t. And omega is a real number. So now we see that it only affects the amplitude. So this one becomes not wave, there is no I here, it's just some number, and it's multiplied by amplitude. So amplitude will change. So this is change in amplitude. Now depending on value of omega, so it depends on this coefficient A here, because K is positive number. It can be, let's say if omega is positive, then it's negative sign here. Oh, it's actually I. Yeah, it's actually positive. So if omega is negative, then this exponent will decrease with time. And if omega is positive, I mean negative, yes, when it's positive, it will actually increase with time. So, and this is a term that's causing instability, right? So if your scheme creates any omega of any derivative with even order that has omega, corresponding omega, this tilde, which is positive, it will increase amplitude and create explosion, instability. So your schemes, basically those are stable, they don't have omega tilde, which are positive. They're all negative numbers. In that case, amplitude only decreases, so there is dissipation. So we don't consider schemes when this amplitude is increasing because they're useless. So, but when we consider schemes that are stable, then it means that these even odd derivatives cause dissipation or reduction of amplitude. And there is no real speed. So these terms don't propagate a signal. What they do, they just reduce. And propagation is done by odd order derivatives. And even odd order derivatives, they just damp the signal. They reduce its amplitude. So we now conclude from this, considering this simple example. Let's summarize it. So truncation error it actually has two parts. It's dissipative errors and those are caused by even order derivatives. For example, second derivative in space. This will cause dissipation. And then there are dispersion errors. So it's odd order derivatives. Like third order derivatives, for example. So truncation total error is the same thing. It's also it's dissipative plus dispersion error, which together is called numerical diffusion. Even though it's a little bit name which is kind of, this is what usually we associate with diffusion, but this is basically a kind of not very consistent name, but this is what term which is used. So people say that this numerical scheme has, of course, all numerical schemes have numerical diffusion, but some of them are mostly dissipative, and some of those schemes can be mostly dispersive. So depending on the scheme, like for example, first order schemes, the leading truncation error, like for our upstream biased, the leading truncation error is second order term, which means that first order derivative, first order approximation of our spatial derivatives in an advection equation will result in a very dissipative or scheme which kind of smoothes the solution, makes it very smooth. While say centered differences, they tend to destroy, average out, because you have, especially when they especially symmetrical, around the point where you compute the derivative, they tend to eliminate even order derivatives in favor of odd order derivatives. So they're virtually not dissipative. So that's why people kind of like those if they model waves. But they have dispersion errors, and sometimes those dispersion errors can be pretty large. So depending on your problem, like for example, if you simulate some flow with shock waves, like engineering flow, not atmospheric science, you don't want these very sharp gradients associated with propagating shock wave to generate all sort of waves bumping around, which are physical. So you tend to use more dissipative schemes. So first order, say, upstream bias scheme is perfect for that task. But if you're talking about, say, propagation of Rossby waves and other kind of large scale waves on Earth, you probably want to use something which is maybe has some dispersion error but doesn't damp those waves, so that those waves just simply disappear very quickly because of this artificial or numerical dissipation. So it depends on the task. Generally in our field, we favor schemes, numerical schemes, that have relatively small dissipation error and and maybe they may have a dispersion error, but we favor dispersion error over dissipation error in atmospheric science at least. Which means that we prefer high order. These errors, you see, this derivative is also multiplied by delta xa square. So when you have higher order approximation, you mean that your truncation error, this dissipative or dispersive truncation error, it's actually proportional to your grid spacing or time step in some power. So the higher approximation you use, the smaller your truncation error and the smaller your errors, dissipation and dispersion errors. That's why people kind of like higher order approximations to represent, say, advection equation, like say third order or fourth order or fifth order advective scheme, and virtually nobody is actually using first order schemes like upstream bias scheme in the field of meteorology because they're so dissipative. So let's look a little bit closer into the nature of dispersion error or error in speed of propagation. We ask ourselves a question: is that error is bad, the most kind of considerable for short waves or for long waves? And that's important because in many cases, if we talk about, say, weather forecast and we care about this large scale phenomenon like cyclones, Rossby waves and other things, we may tolerate small scale errors, but we want to be most accurate for our kind of major phenomenon that we're interested, like Rossby waves and other big waves. So, and of course, long waves or short waves, we actually talk about a relative, in this case, relative to the grid spacing. So if we have phenomenon which has many grid cells or very well resolved versus phenomenon which is not very well resolved when the size is just maybe few of grid spacing. So let's consider one-dimensional grid, and we use this time index m because we reserve our k for wave number. So we consider finite approximation, difference approximation for advection equation. So we move and we consider our solution as some amplitude as a function of time times e I k x, wave number time x, so it's like sinusoidal with wave number k, and x in this case equals to m delta x. We assume that delta x is constant. So then we have a solution that we're looking in the form of some amplitude as a function of time, but here we have I k m ikm delta x. So now we substitute it in this equation and see what actually happens here. So we have d phi over dt e I km delta t delta x equals to minus c. And we use central differences. Let's consider central differences approximation for our space derivative, because that would produce an odd order derivative in a truncation, in the leading term of a truncation error if you expand it in Taylor series. So that odd order derivative would mean dispersion error predominantly than dissipation, and it's not dissipative error. So it's minus c phi m plus 1 minus phi m minus 1 divided by delta x, 2 delta x. So we actually substitute not in here, we substitute this guy to here. Then we have this minus c, and here we have phi of t times phi I k m plus 1 delta x minus phi, not phi, e, minus e to the minus I k m minus 1 delta x divided by 2 delta x. So so now let's cancel it by this term. We divide both sides by this term. So we have the rate of change of amplitude this time equals to minus c. Here it's I k delta x minus e minus I k delta x divided by 2 delta x times phi of t, and it equals to, so this one is cosine plus I sine. So if we subtract, our cosines will cancel and sines will remain, and it's going to be 2 of them. So we'll have a minus c sine k delta x divided by delta x times phi amplitude of t. So here let's multiply by k here and by k here, and so that now we have so now if we get our this derivative equals to minus I omega, because our amplitude is e to the power of minus I omega. If we differentiate it like that, equals to minus ck times sine k delta x divided by k delta x. And well, this exponent will cancel. So we have our dispersion relation that now c equals to omega divided by k, from which we have here that our velocity for like our grid velocity, okay, not mk. So our velocity of harmonic with wave number k equals to this. It's equals to c times sine k delta x divided by k delta x. So we see there is dispersion of waves because our speed depends on wave number, and so it should be, for our original equation should be just c, but here it's modified by this guy. So what's this guy, how it looks like? Well, let's plot it. So we have the following plot. This is our modification factor k delta x. This is k delta x. So we have here pi, here is 2 pi, here is 0. So it will be symmetric, of course, but so it's going to be like looking like the following. So it's going to be 1 sine x divided by x. When x goes to 0, it's asymptotically will move to 1, so it approaches 1. And then when k delta x equals to pi, it will vanish, and so on. But with increasing x, so this is like sine x over x. With increasing x, it becomes smaller and smaller and smaller. So it will look something like that. And so on. Smaller and smaller amplitude. And of course it's symmetrical, because x is now negative, sine is negative, and x is negative, so it's going to be again positive here. So it's going to be like symmetrical. So it's going to be something like this. So you see that now what is k delta x? So k delta x equals to, k is 2 pi over lambda times delta x. So it's equals to 2 pi divided by lambda divided by delta x. So k delta x is of course the non-dimensional thing. So lambda divided by delta x, it's how many delta x's you have in your lambda. So when k is large, it means k is large, it means that this term is small, it means that it's short waves. So here are short waves and here are long waves. So which waves we can resolve on a grid? Obviously we cannot resolve waves that are shorter than 2 delta x, 2 grid spacings. So if you have, this is the wave that you can resolve. This is cosine actually, cosine function, because sine it will going to be 0 here, 0 here, or 0 here. So as if it doesn't exist. But of course you cannot resolve wave like this with just 3 grid points. So the shortest resolved waves not resolved but represented on a grid are 2 r with lambda equal to 2 delta x, so-called 2 delta x waves. And for them, what's k delta x? Equals to 2 pi divided by lambda, which is 2 delta x times delta x. So it's pi. So for shortest waves you have pi. So actually in reality, all this guy, it does not exist on the grid. All we have is plus minus pi. This is only the waves that can be represented on a grid. So you see that in this case, when we use the center differences, we have dispersion such that most dispersive waves, or with the 2 delta x waves, will have 0 velocity, because this guy is going to be 0. And so 2 delta x waves, because you have this c, k equal to c times sine k delta x divided by k delta x. So for 2 delta x waves, ck equals to 0. So when they don't move, they just bump around, but they don't move. And also waves that, like 4 delta x waves. What's 4 delta x waves? It's 2 pi divided by 4 delta x, and so k delta x equals to 2 pi divided by 4 delta x times delta x. So it's equals to pi over 2, those waves. So this is, and so on. For longer waves, we approach 1. So longest waves are k delta x approaching 0. So you have many delta x's in the wavelengths of longest waves. And if you do that, then we see that ck is approaching correct c. So we see that dispersion error is not the same for different waves, of course, but it's actually the biggest error is for shortest waves and the smallest error for long waves. And this is why this is why you need actually resolve phenomena with as many grid points as possible. When you have many grid points, your wavelength is actually contains many grid cells. In that case, your dispersion error becomes small, so it basically becomes not very sensitive to your finite difference approximation, and that's very good news. So even if you have very poor finite difference approximation in terms of dispersion error, your longest big waves, like say Rossby waves on a sphere, they will be moving with speeds that are close to correct speed. So that's a good thing. And those that those waves that relatively short, or they contain very few grid cells within them, so poorly resolved, they will have very relatively high error. So why 2 delta x waves don't move? It's because you average them out. They don't even see this equation, that finite difference approximation. So 2 delta x waves, you have here phi m plus 1 minus phi m minus 1 divided by 2 delta x. And if you have wave like this, you're basically saying that variance here equals this minus this, but amplitudes here are the same. And when you subtract, it's equal to 0. for 2 delta x waves. So for 2 delta x waves, they don't even see this equation. They don't see advection equation, so they're not transported in any way. And that's actually always danger of averaging. When you use averaging operator on your grid, say simple mean averaging, in order to compute certain value somewhere, because some grids can be so-called staggered. So you have, say, some grid points for, say, velocities, and for scalars you have those quantities located in different locations, and in order to compute certain derivatives you need to average. And when you average, you basically eliminate 2 delta x waves, and you may think that it's okay, but the problem is when you eliminate them, but you don't eliminate them from your solution. What all you do, you eliminate them from being able to see your differential equation. So they don't participate in any way in your solution, and as a result they kind of linger around, and that's sometimes not very good thing. So you have a lot of noise. So your averaging can produce actually noise, which is kind of counterintuitive, depending on what you actually use it for, this averaging for. So that's why it's very short waves are not very well represented on a grid, short relative to grid spacing. So the rule of thumb that you need at least say 10 delta x lambda greater than 10 delta x for phenomena that you're really interested. So those that you actually interested, like say if it's storm, say thunderstorm, its size can be say I don't know 50 kilometers or so. Then if you need at least 10 grid points, it means that your delta x should be somewhere like a few kilometers to represent thunderstorm, more or less, or start representing thunderstorms. If your grid spacing is already, say, 20 kilometers, forget about representing thunderstorms on your grid, because they're not really feeling anything which is in your physical equations that you model with your finite difference approximation. So they're completely wrong. So you need at least 10 delta x to resolve. So that's why grid spacing is not the same thing as resolution. Resolution is usually much coarser than grid spacing. You may have 1 kilometer grid spacing, but it means that you can actually resolve more or less is a 10 kilometer phenomenon. And 2 kilometer clouds you cannot resolve, 2 kilometer in size, with 1 kilometer grid. They will be there in your solution, but they will be under resolved and may produce some problems. In addition to diffusion errors introduced by numerical approximation, finite difference approximation to our differential equations, in addition to those diffusion, dissipation and dispersion errors, there is another phenomenon that we can introduce using numerical methods. It's called creation of so-called computational modes, those unphysical modes or unphysical solutions that kind of exist there, and they can distort your simulation quite considerably. To illustrate that, let's consider the scheme which notoriously has computational mode in it, is the scheme that we considered before when we consider stability of numerical representation of advection equation, the leapfrog scheme. So leapfrog scheme so it's a scheme that looks the following: phi m n plus 1 minus phi m n minus 1 divided by 2 delta t equals to minus c phi m plus 1 n minus phi m minus 1 n divided by 2 delta x. So it's centered in time, centered in space scheme, CTCS scheme or leapfrog scheme. This scheme is quite popular, actually, still very popular, but it has this very pesky behavior that produces so-called computational physical mode or a physical solution. To show that, let's return to our stability analysis of the scheme. We've done that before. Just to remind you, when we considered this von Neumann stability analysis, we got the equation that we've been looking, equation for amplification factor lambda. So that looked like the following: lambda square minus 2i sigma lambda plus 1 equals to 0, where sigma is some mu times sine of alpha. Doesn't matter in this case. So we have solution for that that looks like lambda equals to, let me see, that it looks like minus I sigma plus minus square root of 1 minus sigma square. And for stability, we require that if lambda, if sigma is smaller than 1, or it's the same thing that saying that mu is smaller than 1, because of sine is smaller than 1, that scheme is stable, that is, amplitude of lambda is equal to 1. And we called it very good scheme because your amplification factor equals to 1 in amplitude, which means that no additional amplitude is created, like and no, at the same time, no dissipation of amplitude is created by this scheme. So it would seem that this scheme is a very good one. And unfortunately, the scheme is, of course, dispersive, but there is also another phenomenon associated with that. See, we have two solutions here. So lambda has two solutions because it's quadratic equation. We have two solutions, and both of those solutions have amplitude of lambda equal to 1. Regardless of plus or minus, you still have lambda absolute value equals to 1. But one of those solutions, you cannot have two solutions. So one of them is actually a real solution, another one is not a real solution, or unphysical solution, or so-called computational mode. What is that mode? It's actually a solution. The first one, you have solution that is just proportional to two complex numbers, lambdas. It's this one is a real number, so it's plus minus some real number plus or minus I minus IB. So this complex number, where A being some numbers. So you have two complex numbers here. So how they look like on our complex plane. So this is real, this is imaginary. And so first you have solution with, say, with plus. It means that A is positive and B, well, real number. First we consider for positive real, and then you have negative, so it's going to be like something like that. This is some angle theta. So this is one solution. Yeah. And second one is the same negative, but you have now, so negative imaginary portion, but it's going to be negative real portion. So this is another solution. It's also the same theta. So this is one solution, this is second solution. We won't talk now which one is physical, which one is not physical for now. But there are two solutions. Now, let's call them, first solution is it's e to the power of I theta, or minus I theta. That's this solution. And another one is this solution. So it's gonna be e to the power of minus I pi plus theta. It's plus here, yeah. You can actually check it, and it's true. And it's equals to minus e to the power of I theta. So you see it's negative here, and also it's different sign here. So what both of them mean? This one is it's actually to the power of n, because that's what's lambda in the power of n. So with each time step you take n power. So with this guy, there is no problem. You get, this one is e to the power of minus I n theta. And this one is e is minus 1 in the power of n times e to the power of I theta. So so this represents your actually physical solution. Why? Because remember that our solution, it looks like e to the I kx minus omega t, and it's equal to e I kx times e to the minus omega n delta t. So you compare to this is what our, the time some amplitude, this amplitude in this case is a function of x. So you see that this is a correct form. I, n, and theta is like some omega delta t. So this one is a physical solution that moves to the right. Physical moving to right. Now this one is actually solution that, first of all, it's moving to the left, because you see it's a different sign here. So it's moving to the left, but also its amplitude is flipping from time step to time step. So in one time step it's positive, and next time step it's negative. So it's actually moving to the left, and also it has the same amplitude of 1. So physical amplitude of the solution is the same as physical mode, but it's flipping back and forth, back and forth. And so this one is called computational mode. So it's completely artificial. So this is completely artificial mode, which is not physical. First of all, it's moving to the left, and then it's flipping sign from positive to negative. with each time step. So you see, this is not good. And this phenomenon arose from the fact that we have two solutions for lambda. And we have two solutions for lambda because we have 3 time steps here. If we had only 2 time steps, n and n plus 1, we would have only 1 lambda, and so we would have only physical solution. So there is no computational mode for forward in time, say, for 2-level schemes. So no computational mode for 2-level schemes when you use n and n plus 1. As long as you use some other time level, n minus 1, you create computational modes. And sometimes you use even more than that. You can create 2 computational modes. Like if you use third ordered scheme in time, you use time levels n and n plus 1, n minus 1 and n minus 2, then you will have 2 computational modes. So 2 solutions that are not physical. So that's a different phenomenon, and this phenomenon does not depend on your delta x and delta t. It's always present. You will have computational mode regardless of how small your truncation error is. You will still have it. And of course, depending on the scheme, those computational modes, for example, and we'll consider those schemes in the future, that those schemes will have lambda for computational modes that actually is not just flipping like that, but it's actually damped or reduced with time, dissipated with time, and those schemes will be our preference. Because they have computational mode, but that computational mode is effectively controlled by numerical dissipation. So with time, those modes tends to be suppressed. So those schemes are very good ones, but they can be more complicated than this one. But this scheme has computational mode, and then you would ask, why don't people use it still? Well, first of all, people have figured out how to suppress those computational modes as well. So what's artificially? So how you suppress that? First of all, let's consider why this computational mode is arising. Why we have such a weird behavior when it's like solution is flipping around. Well, if you consider this scheme, so if you consider a diagram, the simple diagram, so we have time levels and we have grid in time and space. So let's consider 2 cycles of that scheme, using that scheme. So we have m minus 1, m plus 1, m plus 2. Here we have n minus 1, or n minus 2, n minus 1, n plus 1. So at this level, the scheme that we had this point minus values in this point, and for special derivative we use these 2 points. So this is the pattern that we use for this scheme. And for this point, let's call it cross, we use this point. Oh, let's use this one. This point, then we use this minus this point, and then we use these 2 points. So you see, right away we see the problem here. Our pattern here, on the same time step, for neighboring grid points, we use completely different points, and they completely disconnected. So on next time step, we have again this point, this minus this point, and this minus this, we have this point. So you see with this checkerboard pattern, with each time step, we basically create 2 sets of solutions for even or odd time steps, we have completely different solutions that don't talk to each other. They don't intersect. You always use this kind of checkerboard pattern. So these points came from solution from these points, and so on. So, and these points, you know, they only talk to their set of points. It's like checkerboard. And that's what creates this computational mode, two sets of solutions. And this kind of superposition of these two solutions looks like computational mode. And so how you kind of mitigate this phenomenon? In order to mitigate this phenomenon, you need to somehow connect those two solutions to each other, make them kind of nudge to each other, and that's what. So that's why the leapfrog scheme by itself is never used. You need to use so-called filter to connect those two sets of solutions that this scheme generates. And there are several approaches to that, and we consider as an example a probably most common one. It's used. It's called Robert-Arcelin time filter. I think it's pronounced Robert because it's like French. In English it would be Robert, but I think it's Robert. Arcelin time filter. So it modifies the scheme the following way. So you do step 1. On step 1 you compute your n plus 1 with point m equals to sum this star at n minus 1. So this one is the auxiliary solution. So it's not actual solution, it's just it's aiding your solution, so it's some kind of auxiliary one. And I will explain what it looks like. So minus mu, and here you have phi m plus 1 n minus phi m minus 1 n. So far it looks like leapfrog scheme. Just instead of using n minus 1, you use some auxiliary n1 minus 1. And how you compute it? You compute it at step 2 for next time step. So the following way. This phi n auxiliary n m equals to phi m n plus some alpha phi m n plus 1 minus phi 2 phi m n and plus phi m auxiliary n minus 1. So this is some kind of diffusion in time. You create this diffusion in time with diffusion coefficient alpha, which is empirical constant that you need to find experimentally, but it's small because otherwise you will affect profoundly your solution. So you need some diffusion in time to connect those two sets of solution, but not too strong, so that you wouldn't actually alter the solution itself. So for that alpha should be small, and generally it's in the range from 0.01 to 0. Maybe 1. So in a relatively small range, and you need to find it experimentally. Maybe it depends on your problem. Like if you're simulating a thunderstorm, you may have some alpha, and then you simulate tropical cyclone, that would be different alpha. So you need to find this experimentally. But that approach makes this scheme usable. Otherwise, this scheme is completely garbage. You may not use it because it will produce so much noise. and some ghost solutions. So this scheme kind of makes sure that you damp this computational mode. So this is damping of computational mode. And that's one of the reasons I don't like leapfrog scheme in my research, in my modeling, because of this kind of behavior. I prefer to use find different schemes that already have damping of computational mode as a part of the scheme itself. And we'll talk about that next time when we talk about forward in time schemes, but various order of truncation error. And some of those schemes have already built in this filtering or damping of computational mode, and you don't require this artificial step to apply. But many people use this scheme in their research because of nice property of the scheme that it's not dissipative by itself and has relatively small dispersion error for longer wavelengths. So for phenomenon when you really need accurate representation of speed of waves, probably the scheme is preferred. It's a pretty good scheme, but you would have to use some filter, right, like this Robera-7 time filter, in order to make this scheme work at all. So that's enough for today. See you next time.